Okay, so what did we do last time at the very end? Not that anyone remembers.
Vector V can be written as basis.
So we defined, so we did several things, right? We defined dimension, and I said I had to prove to you a theorem that said the definition makes sense. And then I told you that you could, if you had a set of vectors, right, okay, so we defined basis before that. So script B is a basis for or of, you guys pick your preposition, and you don't have to be consistent. You just can't say to or from, or by, or with.
So it's fairly
Around. So if you have a subspace, a set of vectors forms a basis of it or for it if which two criteria hold?
The basis is linearly independent.
Linearly dependent and span. And they span. And then we said that we had a theorem, which we will do right now, that said if you have two different bases of the same subspace, or for the same subspace, so you have V1 to Vk and W1 to WL, and they both are bases, then what's true?
K equals L.
K equals L. And then what we said at the end of that is dimension of B, written dim, which will open the door for all sorts of bad humor. Is the number of vectors in any basis for V, or any basis of V, is called its dimension. Okay. So, how do we prove it? So how do you prove two numbers are equal?
Put an equal sign between them.
They can't be different.
Analogous to how we prove two sets are equal.
Less than or equal to.
How do we prove two sets are equal in general?
Proving
One
the
is
subsets
they're
are being
both
contained.
Each is a subset of the other. So analogous to that, so analogous to proving that set 1 equals set 2 by showing each is a subset of the other, what I want to do is show you that K has to be less than or equal to L, and L has to be less than or equal to K. Okay? So here's the basic setup for it. Suppose that you have a basis, and you have another set of vectors with L vectors. suppose you have more vectors than are in the original basis. What do you think you can conclude?
What if that was a linear combination of the other?
Then the w's must be linearly dependent. This is perfectly intuitive, but we have not actually said this to this point. So if you're in R3, and you believe that R3 has dimension 3, well, why does it, by the way? Why does Rn have dimension n? If you buy this theorem.
Because it takes n vectors to, at a minimum of n linearly independent vectors to span.
Like this vector.
We have the standard basis. It has how many? N, which has n vectors in it. So once you know that the number it takes to give a basis doesn't depend on which basis you pick, that's what we're proving here, then it follows that you know the dimension. So in R3, we're saying take 4 or more vectors, then they must be dependent. How would you actually prove that to me? If I just, so let me just say, let's do this. Suppose I give you 4 vectors in R3, what argument would you give me based on what we did 3 days
One is a
ago?
linear combination.
But how would you prove that?
You could put them in a matrix, and that could only possibly have rank 3.
So how am I putting them in a matrix?
Just S column.
Put them in as columns, so I have a what by what matrix when I do that?
3 by 4.
3 by 4. So I imagine putting the vectors in as columns. I have a 3 by 4 matrix. What do you know about a 3 by 4 matrix?
You only have rank
Rank
at most 3.
at most 3.
So less.
At least
So
one variable.
at least one free variable. Therefore, if you make this matrix by sticking the vectors in, you know that Ax equals 0 has a non-trivial solution. And how does that tell you what we want?
Because it's seesaw.
How does that tell you that the
There
vectors
is
must be
some
linear?
there is some linear combination of the columns that will give you 0.
Right, so this is like one of the homeworks you just turned in.
Yeah.
The non-trivial solution, say that non-trivial solution is C1, C2, C3, C4, just to be suggestive. And it's not the 0 vector, right? Non-trivial means not the 0 vector. So what does it mean to say A times this vector is 0?
There's a linear combination of the columns.
Linear combination of the columns,
They'll give 0. So they can't be.
groups, these are W's, I guess. Gives you a linear combination of the columns that's 0, and it's a non-trivial linear combination, therefore the vectors are
Dependent.
dependent. So that's how the proof ought to go, except I have to disguise it slightly. So what does it mean to say that I have a basis and I have other vectors?
This should span the same space.
How can I express each one of these vectors in terms of these?
Linear combination.
Linear combination. So each,
Oh, because they're in V, and because V1 to Vk spans V, you can write every vector in.
right, we have a basis for V, I didn't say for V, and you have a set of vectors here that are in V, then each of them can be written as a linear combination of the basis vectors. So each Wj can be written as a linear combination of V1 to Vk. So I can write this, I can do this in either of two ways now. I can write a matrix equation, or I can actually do it in sort of matrix-free notation, which will be useful for the future. So I'm going to say it both ways, but let's do it the matrix way first. So do what you were doing here. Take your W's, put them in as columns. What does it mean to say that each W can be written as a linear combination of the V's?
That each W is a solution.
So I can make a matrix that has the V's in it as columns.
Each W is a solution to.
And then if you multiply that
Matrix
times
times
a matrix of the coefficients of the.
So do I
you
put
get-
the coefficients on this side or on this side?
No, on the other side.
On this side. So if I take various coefficients here, if I wrote that Wj can be written as A,
J.
let's see, what do I want to do? Wj, so I want to write this way, certain number of each V then I can make a matrix A by putting these, whoops, 2, 1, 3, 1, K1. So this would say,
Equals W1.
if I take this many V1s plus this many V2s plus this many V3s up to this many VKs, that's giving me W1.
Then if you take A1.
And then I do the second column,
which will
and it gives me W2. So you end up with a
K
1L, 2L, KL. You have a matrix of numbers, and the coefficients in the jth column are exactly telling you how to get the jth vector W as a linear combination of the V's. You guys with me? So I have a what by what matrix A here.
K
K rows, L columns. And we are saying L is bigger than K. So it reminds you of what we had down here.
rank of A, is it most?
So A is K by L, and L is bigger than K, so what do we know?
There is a free variables.
If you have a matrix with more columns,
But there's gonna be three variables.
there will be
one
free
for-
variables. Because there must be free variables, comma, if you take the homogeneous equation AX equals 0, it must have a non-trivial solution. Let's say C. So there's some vector C, and I guess the C is living in what space here? A solution. How many
RK. RL.
RL? So A times C is 0. What does that tell me about my W's?
There's a linear combination of W's that gives you.
Why? So if I took that combination of the W's, whoops, what do I get?
0.
0. How are you seeing that?
Because you can have the matrix of W's be a product of two matrices, the V matrix and the
So
A.
my W matrix here, we said, was the product of my V matrix with A. That's what we have up there. Right? The matrix of W's is V matrix times A. So what should I do with this equation?
So you should multiply it by C.
Multiply it by the vector C. So I can take this matrix, it's n by L. I can multiply it by a vector with L coordinates. And that's the same thing as taking my right-hand side and multiplying it by the vector C1 to CL. Now what should I do on the right-hand side?
Pull the A out.
Regroup.
Yeah.
You don't say pull out, that's a bad,
Sorry.
regroup is the right thing to say. Because if I now change my parentheses from there to where? Here. I've then got my matrix of V's multiplied by AC, and that's 0. So this linear combination of the W's is the 0 vector. So the vectors are linearly dependent. That's what I wanted. Okay? Now I was gonna say it in a less matrix-oriented way for future purposes, not relevant to today, but relevant maybe today or later. Alternatively, I do have my matrix A. I can write this out without writing all the matrices. I have these equations for the W's. We have A times C is 0, with that same matrix A. And then we're just going to say that each W is given as a combination of the V's, as I wrote up there. So I'm just going to write that in scary notation. How do I write that with a summation symbol?
Summation of A, well, do you want to use A's or C's?
No, I want to use this.
Okay. Yeah, J from 1 to
So
A.
you've got summation A something J, Vj. No, V
B
what?
something.
V something. So how about we put I's there?
And
I from 1 to K.
And I goes from 1 to K.
Summation symbols.
So this is just rewriting that matrix equation in terms of this thing I wrote down here with a summation symbol. So each W can be written this way. And these guys are giving me my matrix that we were talking about. How do I do summation of C's times W? Well, I do summation C's times W's. But now I sum on J. And now you get scared. Because what do we have?
Double summation.
This is, you're gonna be doing this a lot next semester when we do double integrals and triple integrals.
Oh, yeah.
You're gonna have a sum on J and then a sum on I
Or the other way, right?
of this stuff. How in the world can I, oh wait, I looked at C's.
Yeah.
Terrible. CJ, AIJ, DI.
It's a lot.
So that looks scary.
Can't you pull the constant? Well,
But here's what I'd like to do. I really would like to have some coefficient of each VI and then add those up. So I don't like summing on I on the inside. I really want to put the I on the outside. Now, a few of you did an extra credit problem where you were playing around with stuff like double sums like this. So all I'm going to do is I'm going to say, instead of adding up inside, first adding up the i's and then adding up the j's, I'm going to switch the order. I'm going to first add up the j's. And I'm going to just secretly, while you're not looking, I'm going to switch the order of those two numbers. And then I'm going to secretly, while you're not looking,
You're going to tell us that you're doing this.
put in parentheses. What's my coefficient of VI? It's the sum of the AIJs, CJs, J goes from 1 to L. But what is that sum? Matrix A times vector C, ith coordinate is what I'm doing. I'm doing this times this added up. And what do we know about A times C? It's 0. So each of the entries is 0.
So that the whole thing's 0.
So that's 0. But there's a proof that is scarier, but it doesn't involve writing down vectors for the V's or vectors for the W's. All I had to write down was a matrix that encoded how I could write the W's in terms of the V's. So secretly, for reasons that you'll see perhaps later today, this is going to apply to vectors that are in a setting that isn't Rn. So what's looming is thinking about vectors that live in some abstract place and are applicable in physics and chemistry and econ and all sorts of places, but are not living in Rn for some particular number. All right, so that's why I did this. That's the end of the lemma. So back to the past. I tried 2 literary illusions in my other class. I'm going to spare you guys.
There we go.
This is just a movie illusion. All right, so I was in the middle of proving the theorem. I have my lemma now. Suppose V1 to be k is a basis, and W1 to WL is a set of vectors. If L is bigger than k, then the vectors W's must be linearly dependent. Back at the ranch, we had V1 to be k, and what did we know about W1 to WL?
Both the basis.
It's also a basis, B prime, my W1 to WL is also assumed to be a basis. What does that mean in particular?
It's linearly independent,
They're linearly independent.
so it has to.
So,
Ergo, linearly independent. So Mallory, what can I infer from the lemma?
That L is less than or equal to
It
k.
cannot be less than,
Does everybody see that?
yes,
The what logical construct do I do here?
the conjugate.
use over.
If the W's are in fact not linearly dependent but linearly independent, I can conclude
So not negating, so it's
which is contra-positive. So by the contra-positive of the lemma, L is not greater than K. In other words, L is less than or equal to K. I'm half done.
using the
It's the
contrapositive
exact same
again.
logic for the other one. It's the exact same logic for the other one.
Care to elaborate on what you mean by use the exact same logic?
Just relabel your W's as V's and V's
Ah.
as
Yeah.
W's.
Switch the two bases, right? The hypotheses on the basis B and the basis B prime are symmetric. They're both assumed to be bases.
Yeah.
So I can just, by symmetry, switch them. So switching the roles of B and B prime, you now can assume the W's are known to be a basis, and the V's are some unknown vectors. What did we just prove then?
That k is less than or equal.
K is less than or equal to L. If you swapped the roles of the two things, you now would prove that the new candidates, the V1 to Vk, can't have any more of them than are in the basis B prime that we already knew was a basis. So now we're done. So that's that. Okay, so dimension actually makes sense. There is, looming in your mathematical futures, if you go far enough or become chaotic enough, there are whole notions of dimension that are not even integers. So back when I was your age, it was becoming, people were starting to talk about fractals. And people were starting to do research and show that, for example, the coastline of Britain was some dimension somewhere between 1 and 2. Some of you may have heard of something called the Cantor set. Well, it has a notion of dimension. It's a bunch of points. It's an uncountable collection of points in the interval from 0 to 1. It's not 0-dimensional, it's not 1-dimensional. It's got some irrational dimension, which I won't bore you with, but it has the word log in it. So there are more general notions of dimension that apply to things other than vector spaces and vector subspaces. We will not mess with them in this course, but that is looming in your future somewhere if you go on enough. All right, so I want a couple of handy-dandy reference things. Cal actually said something earlier which is nice to know, so let's actually write down useful proposition. Suppose V is a k-dimensional subspace of Rm, and someone hands you k linearly independent vectors. What can you infer about those k vectors?
There must be a basis of V if they're in V.
They must in fact span. They must therefore form a basis. What's the companion statement that I could make?
You have dependent.
If you have set of vectors that spans V, then it's linearly independent in the dimension of V.
You have
So you said you have a set of vectors that span V. Do you want to be a little more
K vectors,
demanding?
K vectors.
K vectors.
Oh, okay.
Okay. Suppose dimension V is K,
No, you're
and you have K
we
vectors
just did that one.
that span, then you can conclude that they must be
Linearly
linearly independent. So this is convenient. Once you have the whole notion of dimension, you've got some power. And you don't have to prove things from scratch every time. Can you guys give me an argument for why this is true?
Because you said so.
An alternative argument.
Because that's you can't span V with a set of a non.
So you're doing the first one?
You need at least K linearly
Yeah, you need-
independent
yes,
vectors to
you
span
need
a
K.
K-dimensional space.
And if there's
But
something
why?
more than K, then it's possible that some of them can be linearly independent.
Okay, you're right on top of it. You're just not quite saying it right. So you're trying to cast this in an argument by doing a proof by contradiction, right? So what I think,
Okay. If V1 through VK didn't span, then you could add another vector, but then you'd have more than K vectors, and so it wouldn't be linearly independent anymore.
but didn't we prove at the beginning of the week that if you had linearly independent vectors and you took something that was not in their span, you could throw it in and they would still be linearly independent?
But that thing would not be V anymore.
Therefore, you have a contradiction.
So we did prove the other day, that must have been Monday, that if you took k linearly independent vectors and you had a vector that was not in their span, then you could throw that vector in and it would still be a linearly independent set. So the proof of the first one is going to be if V1 to Vk do not span, this means there is some vector V in V that is not in the span of the first K. So by our proposition,
You can add another vector.
by our prop from Monday, what's true? If you append, this is very CS-y to do this,
Just add a V.
add another thing to your list, append it to your list,
It's still linearly
still linearly independent. All right, why is this a contradiction?
Because then you have K plus one vectors in a K dimensional space.
Because
If you have K plus 1 linearly independent vectors,
it must be in K plus 1.
either they form a basis, or they don't. But if they formed a basis for your space, this would say the dimension of your V was what?
K plus 1.
At least K plus one.
But in fact, maybe they still don't form a basis. Maybe they still don't span. Well, then the dimension would be even bigger. You'd have to throw in more vectors to get a basis. So the dimension, if the original vectors didn't span, the dimension would have to be at least one more. That's the official proof. Since the dimension of V is K, this is wrong. Right? Contradicting our hypothesis.
Did we state that?
Go ahead.
Did we state that in our hypothesis, or are we just assuming it from back up here?
Suppose dimension.
Suppose
That
you
is
dimension
our
V is K.
I'm
They're
that's what
just-
I'm working on.
Okay, yeah, okay.
So, therefore, the K linearly independent vectors must span. And presumably, this other one's just the same sort of thing. Can you see that one? Suppose you had K vectors that span, why would they have to be linearly independent? Let's see if we can do the other one.
If they didn't, you could eliminate
Good?
one
Keep
or
going.
more, which would mean that your spanning set has fewer than K vectors in it.
So-
So dim V would have to be less than or equal to K minus one.
So if they were not linearly dependent, you would have redundancy,
Yeah.
Right.
which would mean that you could get rid of at least one of them and still span. So I'll let you think that through, but it's correct. If V1 to Vk are linearly dependent, then you can, we actually did argue this basically the other day, then some Vi can be written, well, some Vi is in the span of the remaining ones. Now you start to see why I never use this kind of thing as a definition, because it's yucky to write. Okay, so if they're linearly dependent, you can write one of them as a linear combination of the others. But then you would have fewer vectors spanning the same space. So V is spanned by K minus 1 vectors, which, analogous to our reasoning here, says what?
The dimension must be less than or equal to K.
Yeah, the dimension is at most K minus 1. That's also a contradiction. Matthias, you wanted to say something?
So isn't this just like an if and only if, like, proposition? Is there a special reason why we have like two statements?
Well, because I wanted to have two separate hypotheses and two separate conclusions.
Okay.
So in actual applications, you guys will run across situations where you know you're in R5 and you have 5 linearly independent vectors. Well, then you automatically now can say
They're bases.
Star basis.
they are bases, they span. And vice versa, if you happen to have 5 vectors that span, you would now be able to say, ah, they must form a basis, they must be linearly independent. Now here's something else we're going to actually use more often than I can think of at the moment. Useful observation. Suppose W and is a subset of V, and they're both subspaces. What can you conclude if they have the same dimension?
That,
A set of vectors
that
and
you
then one
can
expand
explain
the
what that
others.
is.
They're the
Morse.
same.
They're the same set.
The basis of one is the basis of the other. Oh, okay.
Yeah. It doesn't,
How should you understand this? Well, you should understand this by saying if W were actually a proper subset of V, there would have to be somebody in V
That was not in W.
that is not in W. Agreed?
yeah.
So what would that mean? It would mean that if you took a basis for W, so that's supposed to represent a basis for W. To get a basis for V, I would have to add at least one more vector by our same proposition that we just used, right? Linearly independent set, vector not in the span, still linearly independent set when you throw it in. What would that say about the dimension of V compared to the dimension of W? It would be bigger. So the only way it can be equal is for W to already fill up all of V. So what was that? That was again a proof by contrapositive. I said, if W were a proper subset of V, then the dimension of W would be strictly less. That's the contrapositive of this. Proof. Use our proposition again from Monday to prove W proper subset of V, which I like to write this way. It's a subset, but it's not equal. That's proper subset, implies dimension of W less than. Now where we're headed on Friday is now starting to look at all sorts of different subspaces associated to matrices and computing all sorts of dimensions. And so you're going to have a fair amount of algorithmic stuff to do. But before we do that, I've been alluding to vector spaces in a more general setting. So I want to talk about that for 10 minutes today, and then we'll do a little bit more on Friday before we go on. What have you been doing with vectors for the last 9 weeks? Adding them, subtracting them,
crossing them,
dotting them,
not dividing them,
not dividing them,
I have no
scalar multiplying them.
Taking the magnitude.
derivatizing them.
So the most basic thing you can do with vectors is add and scalar multiply. So a vector space in general is going to be a collection of objects, pencils, knives, forks, provided you know how to add any two of them together and get another set in your object, one object in your set, and you know how to scalar multiply and get another object in your set. And there have to be certain algebraic rules that hold. Like addition is commutative, addition is associative, there's a zero vector, there's a scalar called 1 that you can multiply by vectors and it doesn't change the vectors. The whole list, and I will remind you, we never really made a big deal of this list, but I will tell you it's on page 7 and 8. So on page 7 and 8, problem 12 lists properties. I think there's 8 or 9 of them. I never remember. 1, 2, 3, 4, 5, 6, 7, 8. 8 properties that vector addition and multiplication have to, scale multiplication have to satisfy.
Are the rules Are vector spaces supposed to sound a lot like the rules for a subspace of Rn, like scalar multiplication and addition?
Well, they certainly have to be, that's what I was saying, you have a set consisting of objects that is closed under those properties.
Okay.
But there's also these additional properties that you have to have that the algebra works. So if you want to see the list written out explicitly, it's on those pages there. It's also, presumably, no, it's not listed in the section we're in now because it says look at that problem on page 7 and 8. So what are things that you have encountered in your lives that you can add to one another or scalar multiply that aren't just vectors in R3 or vectors in R5?
Real numbers. Real numbers.
Okay, but that's R1. That's
yeah.
that's a one-dimensional
True.
Matrices?
matrices. So you've been seeing this notation in homework recently, script m, m by n, the set of m by n matrices. You know how to add matrices of the same shape, you know how to scalar multiply them, and the rules of algebra work fine. In fact, it's sort of boring to talk about matrices because anybody who's worked with arrays in computer science will recognize that really m by n matrices are the same as how many real numbers made into a vector.
M plus
M.
M plus n.
M, n, right? You have m rows, or you have n columns, each of which has m entries. So you could put them into, you could concatenate them and make a monster vector that has all these vectors lined up head to tail.
Yes.
And the properties of adding matrices correspond to adding vectors. Properties of scalar multiplying matrices correspond to scaling vectors. So this is really, it was a nice try, but it's really the same old thing. Other ideas? Functions. So what do you want to do? You want to look at functions from what? R to R, say? Like sine x, or e to the x, or x cubed plus 5x minus 7. Those are all functions. Those are all continuous functions. Okay, guys. These are all continuous functions. But can I add such functions and get another function? Can I scale a function and get another function?
Yeah.
So you can think of functions as forming a vector space, and for applications specifically to differential equations, this is super, super important. And we will do some of that. You could, in fact, also do an interpolation somewhere between this level of abstraction and this, is you could take a limit of vectors in Rn, take vectors with more and more components in them, and I'm going to call that r to the omega, which is going to be the set of vectors that have a countable number, an integer's worth of entries. That sounds familiar. What were we calling this back in chapter 2? One real number for each positive integer. What's that called?
A sequence.
A sequence. So this is the set of real sequences. That's a vector space. You can add two sequences. You can scalar multiply two sequences. And there are various interesting subspaces of that vector space you can look at. Now, I'm going to go on with this more on Friday, but you might want to make sense of dimension. Well, what do you think the dimension of this is? Mn, right? We already said that. You should be able to give me a basis of Mn standard matrices, just like the standard basis for Rn. What do you think the dimension of this is? Feels infinite, doesn't it? It feels like there's an Rn sitting inside R omega for every n by just taking a sequence. I'm writing too small now. Taking a sequence that has all zeros for the end of the sequence. So you can take n arbitrary real numbers for the first n things in your sequence and then do all zeros. Well, this is a copy of Rn. So if it has an Rn sitting in it for every n,
Must be,
then it doesn't have a finite dimension. So the end what I'm going to end with here is the statement that we say a vector space which I'll call script V for the moment, is finite dimensional if some finite number of vectors span script V, and otherwise it's called infinite dimensional. Now, you guys also mentioned things like dot products. We will get to that at the end of the course, and I will talk about, I think, a very important example in mathematics called Fourier series, which is important for all sorts of stuff, physics engineering particularly. So we'll be talking about extending the idea of dot products. So on Friday, I'm going to start with a few more examples of infinite dimensional spaces. And you will have some web work playing around with this stuff a little bit. Okay.